I'm okay like this if you think I've... Hmm? Yeah. Oh, why don't I put... How weird. Mm-hmm. So, do I speak loudly or do we move somewhere else?
No. I mean, in any case, at some moment, if they will not do it, they will not fix it, you can say loudly.
I'll speak loudly. Yeah. Sure. Okay, right. Okay, yeah, but they need it for the Sure. Yeah, yes.
There is a transmission, and they need some voice.
Sure.
Do nas sygnał wchodzi, bez problemu.
Gdzie to jest wyjście podłączone do tej transmisji? zobaczymy, czy coś się zmieni.
Ladies and gentlemen, I believe that all problems are over. And I would like to, yes, I would like to welcome very warmly all of you, and especially our guest who found free time to participate in today's afternoon meeting. The Marian Rejewski, Jerzy Różycki, and Henryk Zygalski computer science lectures have already 10 years tradition. Exactly 10 years ago, the first day of cryptology in January 25th of 2008 began the tradition. Today I have a great honor to announce the lecture, The Hidden Discovery of Public Key Cryptography, prepared by Clifforda Cocksa, who is a British mathematician and cryptologist. He studied in Cambridge and after graduating in Oxford. In 1973, he left Oxford to work for the British government in government communication headquarters, where in 2003 he became chief mathematician. He has also established the Heilbronn Institute for Mathematical Research at the University of Bristol. He has received honorary degrees from the Universities of Bristol, East Anglia, not England, East Anglia and Birmingham. In 2008, he was made a companion of the Order of the Bath. In 2010, he was awarded the Milestone Prize by the Institute of Electrical and Electronics Engineers with James Ellis and Malcolm Williamson. As far as I know, it was the prize number 100. It is worth to add that up to now, around 120 scientists got the Milestone Prize. Among them, Thomas Alva Edison for bulb, Alexander Bell for phone, and Nikola Tesla for electric engine. And in 2014, 3 Polish cryptologists for breaking Enigma cipher. In 2015, our today's guest was elected a Fellow of Royal Society. His research focuses on mathematics and cryptography. In September 1973, during his work at government communications headquarters, he had invented a public key algorithm identical to the one published by Rivest, Schammer, and Edelman several years later. However, this discovery has been classified and remained so until 1997. In 2001, Clifforda Cocksa was developed one of the first identity-based public key encryption schemes. Professor Cocksa, the stage, the screen, and all blackboards are yours.
Thank you for the introduction, and thank you very much for inviting me to speak this afternoon. My subject, my subject of cryptography has changed enormously since I started working in it. When I began, it was something that was done largely by governments, largely in secret. There were something that amateurs perhaps did, and a very small number of academics were interested in the subject. Now, of course, it's a major academic subject. In fact, most of the research is probably done in academia rather than by governments. What's more, cryptography didn't really touch the lives of most people back then. And now, of course, it is ubiquitous. You use cryptography, whether you know it or not, whenever you use your mobile phone, whenever you're buying something over the internet, for example, and you see a little padlock sign come on, you're using cryptography. You're using cryptography if you're sending an email via Gmail, for example. It's all encrypted. So cryptography is now really quite important, and it is around and is used by almost everybody, almost every day. So what I'd like to start is by taking you back to the days before public key cryptography, because public key is in fact the cryptography that is used most widely on the internet. So if we go back to how things were, traditional cryptography, this is this is perhaps typical of, let's say, the Enigma period that we heard about this morning. So we imagine that we have two entities that want to communicate securely, but they're worried, and so they're going to take some plain text, a message, and they want to produce something that they can then send, in this case by wireless in this picture, such that it can be then received and decrypted so that the valid participants understand the message, but someone who just intercepts what's going on in the middle simply sees cipher and can't actually from that cipher work out what the plain text was intended. So the way it is done traditionally is you have a device which turns the plain text into cipher, and you have essentially the same device, or a slightly modified device perhaps, to turn the cipher back into plain. And now you obviously need to do this in such a way that someone sitting in the middle can't also do the undoing process that the the recipient is going to be able to turn the cipher into plain. You need something that stops someone who's intercepting doing the same process. Now, you could do that by making sure that what's going on in turning plain into cipher, what's going on in turning cipher into plain, is secret and is not known by the interceptor. But that's a risky thing to do, because if you if one of these devices, and maybe there are many around, gets lost, then of course the whole system is insecure. So what you do is you have you arrange it so that actually you don't need to keep this process secret. You might want to try to do that because it adds to security, but you will arrange your security so that you do not need to make the process of encryption and decryption actually secret. What you do is you have some additional secret called the key, which is used somehow in this process. Some setting that maybe you can change every day or every week, depending upon sort of security you want. And it's this that you keep, that you apply the maximum security to. And that roughly this process is really how all cryptography works. Even if it's a paper and pencil system, you still essentially have some process and a key which can vary from time to time. I mean, even the Caesar cipher is like that in a sense, in that the process from turning plain to cipher is very simple. You simply shift each character by some hidden number, and the hidden number is the key. That's not very secure, but it shows that even something as simple as that uses the same process. Okay, so now if we move on to the problem that GCHQ and other intelligence agencies and security agencies were faced with in the 1960s, was electronics was getting cheaper, and that meant that you could apply secure communications further down the chain, so that if you were instead of having just high-level communications of, say, the military protected in this way, devices were getting cheaper, there were more of them, and so you were going to have more devices, but more especially more keys. And if you think about what you might want to do there, if you have n entities on the communications net, you may well want to have a separate key for each communication pair. So n entities in a net means half n squared keys are needed. And as n gets bigger, that grows quadratically. And what was becoming the case in the 1960s, and one could see it getting worse, was that this process of keeping your keys secure was getting increasingly expensive, and in fact was becoming the most expensive part of a secure communications system. The point is, not only do you have to, let's just go back one slide, you you need to get these keys, the same key to both sender and recipient. You have to do that in a way that's secure, so you can't send it by using the same mechanism. Furthermore, once you've got the key, you've got to look after it. And once you've used it, you need to make sure you destroy it securely, because if you were to, even after it's been used, if it were discovered by someone intercepting the message, they could use it to at least understand old data, old traffic. So key management was becoming a real problem. And so what we realized that we needed to do was to do some research into how can we make key management, secure key management, cheaper. That was the motivation. And therefore, we needed some new ideas. And in the late 1960s, this job was given at CSG. That's the part of GCHQ that is responsible for devising security devices, was given to this chap, James Ellis. James was the sort of person you would give problems to if you wanted an off-the-wall solution. He liked thinking about outside the box. I mean, that was kind of what motivated him, was finding new ideas. You wouldn't give him a problem where you knew you needed a definite answer by a definite date, but if you wanted some new ideas, he was a man to go to. And so he was given this problem of can we work out how can we make key management cheaper? I suspect the management of CSG of the day was probably thinking in terms of relatively conventional solutions based on things like key distribution centers, sort of devices that were themselves secure and could somehow send keys out in a secure way. But that's not what James came up with. He looked at the problem and came up with this observation. He said, and this is from the paper which he wrote up his ideas. Although it's generally regarded, he said, as self-evident that you have to have some initial information kept secret from an interceptor, you didn't need it. It was possible to send secure messages even if the method of encipherment and all the transmissions are known to the interceptor and nothing is shared in secret beforehand. Now, that was a totally revolutionary idea. I mean, if you think about what that actually says, we have two entities, they have nothing shared in secret between them, and someone's going to hear absolutely everything that's going on between them. At the end of whatever they do, they will have shared secrets, and yet someone in the middle has seen everything that's gone on between them. And that sounded almost impossible. But James had, one other thing about James was he used to read lots and lots of papers about all sorts of things. And he'd come across this paper from sort of a wartime Bell Labs report, which was an idea for essentially communicating over a wire. So the idea would be that there'll be a sort of physical wire connecting two entities, maybe a mile long, a few miles long. This is sort of battlefield type cryptography. And the worry was that someone could actually sort of tap into the wire in the middle and hear what's going on. And the idea was that you could make this secure by the person receiving the message put random noise onto this line. Okay? So that if someone listens to what's going on between these two entities, all they hear is noise, because the noise is so loud it drowns out the true signal. But because it's the receiver's put the noise on, the receiver can also take the noise off and therefore recover the message. That was the paper. Now, there are actually reasons why, in fact, it's been tried since, it doesn't really work. There are ways around this. This is not actually a very good idea. But James was fascinated by this and thought maybe the digital way of doing this. And he came up with what he called a schema for implementing his idea of what he called non-secret encryption. So the idea was that you would have three processes. I've called them M1, this is what he called them too, M1, M2, M3. And so we have the sender wants to send a message, we have the recipient over here who wants to receive something. And just as in that analog system, it's the recipient who starts the process off, in this case, with the secret. So this, in a sense, is the analog of that noise being added to the wire. This is how James saw it. And we'll put this through some process he called M1 to produce an enciphered version of the key. There would then be a process M2, and this enciphered key would be used to encipher the message. And that produces an enciphered message. And so someone listening to it in the middle gets the enciphered message and the enciphered key. But to decrypt, you don't use the enciphered key, you have to use the original key and to undo the encipherment. So you can see this is a direct analog of the physical system. And this was how James said, well, this could work. He had a sort of digital way of doing it, which I'll show on the next slide. But it's not actually a practical system in any sense at all. I'll explain why. So what he thought of was having the process M1 is simply a permutation, a hidden permutation of numbers 1 to n, and that gets sent to over to the sender. The recipient starts, as I said, and applies this permutation to k. The sender has got this code book, if you like. It's an n by n code book. So there are n possible plain text, n possible keys, and you look up the cipher in this code book. But there's a corresponding M3 code book which uses not the enciphered key, but the unpermuted key that essentially undoes that. Now, this is not actually in any way a practical secure system. It simply functionally works. For a start, for this to have any sort of security, n's and m's would have to be 2 to the 100 in size. So we're talking about a code book of 2 to the 200 in size. I mean, that's not actually a practical proposition in any sense. It's more work to store than it is to actually sort of undo this whole system. So it's just showing you that mathematically, functionally, you can find functions M1, M2, M3 that does what James wants to do. But it is not in any sense a solution to his problem. Find a practical way to do it that's secure. Now, this was in the late 60s that James came up with this idea. And this was before I joined the organization. But that meant that we knew there was this system we would like to find a way to actually instantiate, to find a solution to. How do you make it practical? Well, it was given to a number of mathematicians in the department to look at. There were also some in the department who thought, actually, it's not possible to do this securely, and actually try to find proofs that you couldn't do this. But the approaches that people took to try to find solutions they probably tied themselves too closely to James's original idea. They were trying to find, in a sense, mathematical ways of instantiating James's codebook method, and basically couldn't find a way to make it work. Looking back at the papers, they got quite close. They got methods based on modular arithmetic, but they hadn't quite got the right function. So they actually did get quite close to finding a solution, but didn't find something that worked. And then, so I said the main problem was perhaps tunnel vision, being too closely bound to the way James was seeing it. And I was quite lucky that I arrived in the department after doing research in number theory in September of that year. And as part of sort of getting to know the department, I mean, not only was I told sort of the work I was supposed to be doing, the day job, but various sort of interesting, odd problems that were around that were explained to me. And one afternoon, I was sort of shown, you know, Ellis's problem. Can I? And luckily, had it explained to me by a mathematician then, Nick Patterson, who explained the problem not in James's terms, because James's, which would have again made me think the way James was thinking, but explained the problem entirely mathematically. Find these functions m1, m2, and 3 that have got these properties. So I was able sort of that evening to think about the problem, and because I'd been working in number theory, I was quite lucky that actually the right solution came to me. I wasn't able to write it down, of course, because you weren't allowed to, so I had to sort of go to bed hoping that when I woke up in the morning I would still have the idea in my head. I wouldn't think I just dreamt it. So here is the solution. Whoops, have I gone too far? Yes, I think that's right. Which does actually follow, James's method. So because I've been working in number theory at Oxford, I thinking about what might make an M1 process, something that is essentially a one-way process. Well, it seemed to me multiplication of primes, because we know that it's easy to multiply two primes together. It's much harder to undo that and to factorize numbers. And back then, the best method for factorizing was a number n was of order 4th root n. Of course, we have better methods now, but it's still much harder to factorize than it is to multiply. And so then, that seemed natural for M1. The question is, what would make a reasonable encipherment process for a message M? And the idea was, well, we can raise M to a power, and I was thinking that we'll just have the 1n as the secret, so we'll raise M to the power n modulo n. And the point is that it seemed to me to be hard, and that is still the belief, that it is hard always to undo an explanation of that exponentiation of that sort if you don't know the factors of n. So in other words, this is, as long as the numbers are big enough, secure in that if you see m to the n mod n and you know n but you don't know its factors, then recovering m from C is hard. But if you know the factors of n, there is an exponential, a power d, which you can compute c to the d mod n, and that actually equals m. So it undoes the encipherment process. So that fits the James model. And I'm sure all of you know, but I just it's also very quick to exponentiate. Remember, these numbers n are going to be very large. Back then, we were thinking of 400 or 500 bits. And these days, we use perhaps 2,000 bits. but you can raise something to the power of a number of 2,000 bits by successive squaring and multiplication. So it's logarithmic into the size of n. So raising something to the power of n is work that's only logarithmic in n. So it's feasible, it's not expensive. Okay. And how do you decode? That's actually the details of the mathematics there, because you know P and Q, which multiply together make n. As long as P and Q minus 1 and Q and P minus 1 don't have common factors, you can find a P dash such that P dashed is congruent to 1 mod Q minus 1 and QQ dash is congruent to 1 mod P minus 1. Euclid's algorithm does that again. It's logarithmic in terms of the work involved. And then by raising something to the power, by raising your cipher to the power P dash mod Q and Q dash mod P, you can recover M mod P and M mod Q, and if you've got that, then you can recover M. And you can actually combine all that into one piece of work by saying there's actually a D such that C to the power D mod N equals M. But you can do it separately, mod P and mod Q, and then recover it. But the point is that it's actually relatively quick to do that. So we had something that seemed to satisfy what James wanted, and this is just a summary of the security aspects of it. The work to be done via the encipherment process is relatively inexpensive. It's fast to create and find primes. There are lots and lots of primes, and it's quite quick to test if something is prime. Multiplication is fast. Modular exponentiation, as I said, is also fast. By that I mean logarithmic in the size of the numbers you're trying to deal with. On the other hand, factorization, which seems to be needed to actually do what the work of an interceptor needs, is slow. The best algorithm these days is the number field sieve, which has that rather unattractive formula for the amount of work. But in summary, if you think of n as being a 2,000-bit number, this comes out to be over 2 to the 100 in terms of work, so way beyond the work that anyone can do. So you can find n's for which that is above what anyone can achieve, and yet that's quite doable. So we had a practical system. But things didn't come in ones, they came in twos. Malcolm Williamson, who shortly afterwards I was actually sharing a house with him, he'd actually joined the department a year before, someone I'd been at school with, and then I'd been at university with. And I happened to mention that I was about to publish a paper, which he thought was quite surprising after only having worked there for 2 months, and he hadn't published one after being there for a whole year. So I explained to him what the problem was and what I'd done. And he went away one night, and the next morning, it was the only morning I'd ever known him leave for work before me. And he had come up with a completely different solution to the same problem. But this time, he didn't even follow James's structure, because I hadn't actually explained James's structure to him. I just explained the basic problem. And Malcolm had been working in something called shift registers, linear shift registers, and because these were at the time a component of pretty much, no, not all, but a very large number of cryptologics used quite widely for creating secure communications using the conventional methods. And the idea, basically, of a shift register, it's a sort of cheap counter. Remember that these are the days of electronics where it kind of really mattered how big how complicated your combining functions were. So essentially the idea is that you have a register that is composed of bits, ones and zeros, and to step it, I've shown a very simple example, but essentially there's some fixed set of positions that you XOR them together. That gives you your new value, that gets put in at the end and everything shifts along one. So it's a cheap component, cheaper than adding, and if you get it right, it gives you, if this is n long, you can get a sequence that, if this register is n bits long, you can get 2 to the n minus 1 long sequence. So essentially, it performs a function of a counter, but less expensively. So you've been working with those extensively. One thing we knew was that the what we call the distance problem was a difficult problem to solve. In other words, it was computationally expensive. And that is, if I give you two different fills, remember I've just said that basically if you get this design right, every single pattern apart from all zeros will appear at some time. How many steps is it between two different known patterns? It's called the distance problem. And it was known that that was a difficult problem. But the thing is that this can be represented algebraically using a notation of finite fields. So here's how the algebra works. We can define addition of two fields basically by XORing them together, so that we take each bit in turn and XOR. So if I were to XOR that with 1 and all zeros, I'd simply change the value of that, and these others would not change. That's how you add. You can think of moving one step as being multiplication by a constant. And once you've got that, then of course that defines the whole multiplication process. So you can now define a whole multiplication of what you mean by multiplying two different fills. And that essentially is exactly the same as the way you would define a finite field over a binary finite field. So that was what Malcolm was familiar with. And he came up with a process. I think I'd rather show you the structural picture first, and I'll go back to the mathematics. So his idea was that it was a three-step process rather than the two-step one, which I described before. So again, we now have a sender who wants to get a message to a receiver, and now it's the sender that starts the process. And the sender has a message A, which he represents somehow as the fill, the content of a shift register with of length P. And he actually thinks of a random K. And remember, we now have this algebra, so that we know what multiplication means on these things. So he produces B to the power K, A to the K, and he sends that. The recipient takes that and raises that to his own random value L, so produces B to the L, which is A to the power KL, sends to the sender. The sender is able to because he knows his little k, he can find a capital K, which essentially undoes that process, so that capital K is congruent to 1 mod P. Remember, P is the length. When I say length, that's the length of the full cycle, and sends D. And then the receiver can take off the L by raising it to the power capital L and gets A. And so someone in the middle sees A to the K, A to the KL, A to the L, and it's believed that's called the Diffie-Hellman problem now. And we thought it was hard, and time seems to have proven it, that it's hard from that to recover what A is. So if I just go back one slide, that's actually the mathematics of it. You raise A to the power K, then raise it to the power L, and now we find the sender knows a little capital K that is congruent to 1 mod P, the length of the cycle of the shift register, and calculates a D, which is C to the K, which is now A to the L, and then the recipient can essentially do the same thing with the L and get back to A. And then a little bit later, Malcolm Williamson came up with a neater idea of enabling two participants to share a secret. This is actually identical to what's now called Diffie-Hellman. The sender recipient basically agrees some initial field X. The sender will then compute XDA for some random A and send it. The other side will think of a random B and send it. Now the point is that they can then both generate X to the power AB. X itself does not have to be secret. He came up with this in autumn of '74, but it didn't get written up for a little while afterwards. In fact, not for another couple of years. Malcolm wasn't very good at writing things up, basically. And so this is the picture of that, and it is just like Diffie-Hellman. Sender sends X to the A, recipient sends X to the B. The X is not secret, but the A's and the B's are, but both can then calculate X to the power AB. The sender by raising that to the power A, and the recipient by raising that to the power by raising that which is received to the power B. So they end up with a secret. Now you might wonder, what's the point of them both knowing something that they haven't agreed beforehand? It's just a random value. Well, the answer is that can then be used as the key for a conventional crypto system, which was the whole point of the thing in the first place, was to find some way of managing keys. Okay, so at that point we now had two ways of implementing non-secret encryption. So what did we do with the idea? It's not true we just buried it. That really is not. It's not a fair picture of what happened. First of all, CSG looked at, can we actually implement this? Is it practical? They preferred the Williamson method because it was cheaper to implement. We were very familiar with shift registers. We knew how to make them. They were relatively cheap to do. But one of the things that we had, in a sense, we did miss was the fact that how do you apply authentication to this? I mean, this is a way in which two entities can share a secret, but how do you know that you're talking to a valid person and not someone masquerading if you're trying to create a new secret? There was a question about patenting that was taken quite seriously, but the advice we got at the time was that this is mathematics, and therefore these ideas are not capable of being patented, and you would fail if you tried to patent them. Things have moved on since then, and of course we now know how to take ideas like this and embed them, if you like, in a physical device and patent them. But back then we didn't, and our patent lawyers said, no, you can't do it. But fundamentally, the technology of the 1970s was really not up to actually making this practical. It was still too expensive. And the techniques were not made public. There seemed to be no reason to do that. But we didn't just sit on them ourselves. I mean, we certainly shared the ideas with our partners, so that the ideas were shared, for example, with the NSA. They were shared with the Institute of Defense Analysis. So, though it wasn't just kept very tightly secret, it was shared pretty widely throughout the sort of intelligence communities. But for the moment, that's really the end of the CSG story, because not that long after, a year and a bit after, came the paper of Diffie and Hellman called Multi-User Cryptographic Techniques. That came up with the concept, and it was described in terms of we want a decrypt process, we want an encrypt process, such that D and such that each one will undo the other. And essentially, it described public key, or non-secret encryption, as we were calling it, in structural terms, but without any way of implementing it. It was just what could you do? But in addition, there was one additional thing in their paper, which was they showed how if you had such functions, you could use it for authentication. You could use it to produce signatures. And so once we saw that, James sort of said, right, now we know how to solve the authentication problem. So once we saw that, we knew that we could use the our ideas to provide digital signatures. And then came the paper in November '76, New Directions, which added to their first paper and gave the what was Williamson's second method, the one which by then he had written it up, but had not been written up back in 1974, which is now called Diffie-Hellman. So in '76 they came up with a practical way of creating keys. And then, so that is Diffie-Hellman, and you can see it's very much the same as Williamson's second method. You have a group G, and in the original paper they were talking about multiplication modulo prime, so not the shift register based, but mod P based. And so and it works for any group. We have a group and the generator G, and I'm now using what's now the standard notation for public key. The two communicators are called Alice and Bob. They're always Alice and Bob. So Alice chooses the secret A and publishes G to the A. Bob chooses the secret B and publishes G to the B. And they then share this common secret, which is G to the power AB, which they calculate in two different ways. And in the case of multiplication mod P, again, discrete logarithm is hard, and actually the work factor is very, very similar to the work factor for factoring numbers of the same sort of size. It's not quite the same, it's not quite the same process, but algorithmically it's very similar. So that was Diffie-Hellman. And then, and that's a picture of it, which is really very simple. It's something you can keep in your head. That's how you share a secret. And then came a second rediscovery, the reverse Shamir-Edelman paper, a method for obtaining digital signatures and public key crypto systems. So basically, reverse Shamir and Edelman had seen the challenge, if you like, in Diffie and Hellman's first paper, find these functions D and E, which commute for D for decryption, E for encryption, which can give you a public key system. And they came up with what was actually very similar indeed to the original, what I've just described. The key is 2 primes. The secret key is 2 primes P and Q. The main difference is that when I published the paper, I assumed that the exponentiation E was actually equal to PQ to minimize the amount of key material, but they allowed it to be anything. And then there's a corresponding D, which undoes the encryption. And so E gets sent across, and that's not secret. And the product PQ gets sent across to the sender, and then the message is raised to this encryption power E, which is public, to produce C, and then you decipher by raising to the power D, and the point is that D is a secret. You can deduce D from E if you know P and Q, but to deduce it from knowing N is hard. So that's essentially, that's RSA, and it's essentially the same as the original idea, but entirely independently discovered. And it's often thought of as being the mathematical equivalent of this physical thing called a padlock. If you think of it being something that anyone can lock, and only if you keep the key can you unlock, think of sending across a padlock to someone. If Alice wants to get a message across, Alice wants to receive a message from Bob, what Alice will do is create a padlock, which is the N and the E, open padlock, sent to Bob, but keeps the key for himself. Bob takes the message and then locks it with the padlock and sends it to Alice, who can then decrypt using the key. So that's kind of a nice physical way of thinking about what's going on with the RSA system. It's a digital way of implementing a padlock system. And the nice thing about this is that you quite easily get authentication, because authentication basically means something that if I have a message, what can I do to convince you that it was me that sent it rather than somebody else? And you do that with a digital signature. So we assume that everyone knows your public key, and so what you can do is you take a message, you apply a one-way function to it, a secure hash, to produce some small value C, which is between 0 and n. So you need some secure hash function so that you can't go back, or you can't produce. If I see a C, it's very hard to find a different M that produces the same C. You need it to be one way. And then you use the private key to calculate the signature, which is C to the power D mod n. And because D is secret, only the holder of that secret can produce the S, and you append that as a signature to M. Now the point is that if you then receive an M and an S, a recipient can then compute C and can then take S to the power E and check that's equal to C, because this is the public face, if you like, of the signer, and check that you get the right value. You need F to be, as I said, non-invertible and collision-free. And so that gives you a way of signing. Okay, so that's really the story of the discovery and sort of the rediscoveries. I just thought I'd try to. I mean, since then, cryptography has, as I said, become a much bigger subject, and there's been a kind of explosion in the theory. There have been lots of new public key systems discovered, although RSA and Diffie-Hellman still remain the ones which are used for most purposes. We now have lots of protocols which basically define how should you use public key, define them precisely, because if you get it wrong, it's actually quite easy to put in weaknesses that you didn't expect to happen. And one of the stories of the last 40 years or so has been discovery of all sorts of different ways in which if things aren't implemented quite right, you get attacks, you get weaknesses. If, for example, your message doesn't have quite enough entropy, you don't put randomness in the right place, then you can have a weak system, for example. So there were lots of surprising ways in which these systems can fail, and you need to understand those. And it also, some of the public key systems that were sort of discovered, for example, knapsack systems, were later found to have surprising hidden mathematical weaknesses. So it's not that easy to come up with a secure public key system. And one of the things that tends to be looked for now, if someone comes up with a new system, is a mathematical proof of soundness. And by what that means is you state that breaking this system is equivalent to solving this mathematical problem, and here is a proof that these two things are equivalent, and you look for that. And if you come up with a new public key system and you can't find some sort of proof of equivalence, it's actually quite hard to get that to be published. But it took time for technology to catch up. But by the early 80s, there were devices that used public key, and increasingly software applications, standards emerged, and now it's now a very sort of mature subject. I'm just going to mention a couple of developments that are kind of quite important because they really are used quite extensively. One is, I mentioned that Diffie-Hellman will work on any group, but of course to be secure it's got to be the right group with the right structures. This one was discovered in the mid-80s, independently, again twice. Everything seems to get discovered twice, it seems to me, by Neil Klebitz and Victor Miller, more or less at the same time. Which is the idea of using elliptic curves as the group. And the advantage of elliptic curves is that you can get away with much smaller messages, because security of discrete logarithm on elliptic curves is to get n bits of security, so 2 n bits of key. You don't have this sort of more sub-exponential-like attack that you have with factoring or discrete log mod p. So because you can get, because of that, you can get much shorter overheads in terms of messages. I do have time just about. I will to show you how elliptic curves work. The back line is quite hard to see, but if you draw an elliptic curve like y squared equals x cubed plus ax plus b over the reals, it typically can look something like this. And what's surprising, and can be proved either sort of rather painfully using sort of standard mathematics or more advanced maths gives it straight away, is that there's a group structure here. That if I have 2 points on the curve, I can define the sum of those 2 points. And I define it this way. I join the 2 points. It's a cubic curve, so it must meet the curve somewhere else. And I reflect it in the origin. And that plus that equals that. And that defines a group structure. And it's quite surprising in a way that satisfies associative law, for example. It's not obvious at all from that picture that's true, but it does. Now, you wouldn't want to do it over the reals if you're doing cryptography for many reasons, but you can define this curve over a finite field, for example, modulo p, and if you still have the group structure, it still applies, and that is what you use for cryptography. And just an example of why it kind of might matter these days, Bitcoin uses ECDSA, that's the elliptic curve digital signature algorithm, and it uses this curve, y squared equals x cubed plus 7 modulo that number, which looks rather nicer in binary than it does in decimal. So if you can solve the discrete log problem in that, you can hijack any Bitcoin wallet in the world. So elliptic curves are used. In terms of public key attacks, perhaps the most significant one is Shor's algorithm, in which he said, well, if you can build a quantum computer, it's actually going to break actually pretty much all of those systems I've just described. And the way, roughly speaking, I mean, quantum computation is a sort of lecture on its own, but roughly speaking, what goes on is that if you've got n quantum bits, n qubits in a quantum system, you can think of operating not just on an n-bit value, but on 2 to the n different values at the same time. You load a register with... the register, in a sense, holds these values probabilistically. And at the end of the calculation, you sample, and you just get one state back according to the amplitude of those probabilities. And if we could build a big enough quantum computer, we could break public key. The point being that a Fourier transform is a unitary operation. And so here's roughly how Shor's algorithm works. To factorize number n, you need a register which is about n squared in size. So if n is 2,000 bits, you need a 4,000 qubit register here. And the point is that you can calculate all the x to the a's for all of those 2 to the 4,000 values, which is kind of the magic of a quantum computer. But then you do a Fourier transform on the a values. Well, no, you first of all observe a single x to the a, and now we get a lot of values of a, all having the same value mod phi of n. And then you do a Fourier transform, and that reveals phi of n. And once you know phi of n, then that allows you to work out the factors of n. So, but to do this, you're going to need 4,000, and you need the A register as well, 6,000 bit quantum computer. And I think it was recently announced that IBM have only managed to get a 50-bit quantum computer working. So there's a bit of a gap between 50 bits and 6,000, but that's it. So where are we now? Well, lots of work going on in public key. These, I think, are 2 of the most active areas. One is trying to find replacements for Diffie-Hellman and RSA, because of the fact that Shor's algorithm solves factoring and discrete log in polynomial time. There are ideas out there. Some of them look pretty good. They're not as efficient. They're not as elegant, perhaps, as RSA and Diffie-Hellman. There's a feeling that maybe there are better systems, perhaps. So there's still more work to be done to come up with what we feel is, this is the right one to go for. But at some point, we are going to want to have, we're going to need a replacement, probably, unless there is some really fundamental, something fundamental that stops a quantum computer being built of an arbitrary size. And that's still, I think, a question that's up for grabs. And the other area that's actually very interesting and would make a good talk on its own is fully homomorphic encryption. Essentially, that's one of the things, for example, with RSA is that if I have encrypted a value, I can very easily compute the encryption of say, its square. Or I can, if I have an encryption of 2 values, I can compute the encryption of the product because of the way in which RSA works. But I can't easily compute the encryption of the sum without doing a decryption first. What you'd like is a way in which you can manipulate encrypted data without doing decryption, which would be good for cloud computation. Now, there are methods for fully homomorphic encryption, but they are quite slow. The best methods now take perhaps days to do things that would take fractions of a second, not done homomorphically. So there's a big gap between where we'd like to be and where we are with homomorphic or fully homomorphic encryption. And so that's another quite extensive research area. So that's the future, if you like. So that's the end of my talk. So I've kind of given you largely history and then tried to bring it to some extent up to date. And very happy to take questions.
Thank you very much for your extraordinary and excellent lecture. Now it's a time for a discussion. Are there some questions, comments, or remarks?
as you said, that time or your discovery, you share these results, your results with NSA.
Mhm.
Yes?
Yeah, that's correct, yes,
Yeah.
we did. Mhm.
So they know when Diffie-Hellman announced with their results, their paper, New Directions in Cryptography, so NSA knew that it was earlier discovered.
That's correct, yes, they did.
Yeah.
Mhm.
So it's sad. To some sense, it's sad since you lost the fame. Now you have the fame.
Oh, sure.
And also you lost the money since they earned it a lot of money on it.
That's true.
So it is not disproved that RSA or your algorithm can be solved in classical way. I mean, without quantum computing, right? I mean, it's not disproved that we can solve RSA in classical way. I mean, without the quantum
That's true. I mean, it is one of the slight frustrations that there's never been a proof that breaking RSA is equivalent to factoring, but no one's actually managed to get there. Yes, I mean there are methods which are provably equivalent to factoring, but they're more cumbersome. And the first of these proof systems was, I think, Gilvas and Macaulay, where their encryption system was provably equivalent to the quadratic residuosity problem. But I mean, as an example of how less efficient that was, that produced that communicated one bit securely for the amount of work, same amount of work as RSA communicates the whole n bits. So there was a penalty to pay.
So, second question, short question. If somebody breaks it now, how the world will change? Somebody say, you or somebody comes with a solution, how the world will change. I mean, what will happen? So what will happen to the world if somebody comes and say, well, the RSA is solved.
Well, I mean, there are lots of other systems that could be put in place, but it would be a concern because it's very widely used. It would be a shock. Yes. Mm-hmm.
Even the proof of the hypothesis, even the proof of the hypothesis that P is equal to NP. You know this hypothesis. No.
Oh, you mean it's P and NP?
Yeah.
That's true. I mean, we don't actually know that there exists a secure crypto system, period. That's sort of true, but
it will not give any concrete algorithm how to break RSA. It would be just a theoretical result. It is to prove this hypothesis. It in fact is not practical.
It's not obvious to me that it's not that there's no reason why there might not be a proof that solving RSA is equivalent to factoring. As I said, I mean there are systems where there is a proof that breaking the system, if used in the right way, is equivalent to solving a known mathematical problem. It's believed that RSA is equivalent to factoring, but it's not been proven. It's not obvious that there cannot be a proof of that.
So you start your lecture with referring to Alice, his revolutionary idea who created a new paradigm in cryptology. So could you point out the moment of cryptology history when such a new paradigm like this, something of type of Alice paradigm were created, we change our view of cryptography? So I guess this Feynman and Shor quantum cryptography was such a revolutionary idea. But could you point out some other ones? And even more importantly, could you point out the field where we need such revolutionary ideas which will possibly create a new paradigm for cryptography?
That's quite a big question. I mean, looking earlier, I would say that the use of mechanical encryption over paper and pencil systems is probably a paradigm change. You quite rightly say what Shaw did sort of changed our view of security, of potential security. I'm not sure there's been paradigm shifts. I mean, there's been a lot of development, and for example, something I didn't mention was all the various things you can do with cryptographic ideas. For example, some of the interesting things you do with multi-party computation, that you can, toss a coin over the internet, for example, without actually seeing the person at the other end or trusting them. I mean, so there are clever things you can do. So I think it's been very much developmental, but there's a lot now that cryptography enables you to do if you wish to do it.
Other questions?
Can you recall, perhaps, what was James Ellis's first reaction to your discovery?
He was really, really pleased because, I mean, there was a sizable body of people who thought that actually these ideas were not going anywhere, they weren't practical, there was a reason why it wasn't going to we wasted a lot of time looking at it. Yeah. So, I mean, I would say he was over the moon, to use an English expression. That actually, his ideas, which people had thought were a bit cookie, actually worked.